Hi, folks. Yes, so DINO, it's a family of models that have been around for about 4 years now. DINO is distillation with no labels. This is as opposed to weakly supervised learning that was sort of dominating the Vision Foundation model space at the time. And they wanted to get away from things like contrastive labels or weak labels. And that's essentially what they did across these 3 papers. So it's a purely self-supervised learning approach. It's inspired by similar work, as is often the case in computer vision. We are the late to the party, follow what the language people are doing, because obviously most of the money seems to be in language still at the moment. And essentially what it does is it takes a lot of things that we're familiar with in supervised learning and it adapts it so that it can make use of it to learn sophisticated representations. So in particular, we've got this idea of prototypes, which are basically what happens when you take the classes away from classifiers. And it learns essentially to, instead of classing things by labels, it learns to try to separate and cluster things on a kind of evidence base based on the distribution of pixels that different things have within its data set. We'll kind of touch on that a bit further. It uses a teacher student with exponential moving average. You don't have to, it chooses to do so, and it does so for a few reasons we'll get into. It uses a combination of losses, and really the DINO to DINO v3 story is a story of like it's a very engineering heavy effort where they take an awful lot of small incremental improvements from other papers and sort of bolt them all together and find ways to make them work with each other and find the training regimes in which these things work. And you can see some of the things which have gone into it. We've got 2 losses, the principal losses for DINO. We've got this multi-crop training regime, which come from swapped assignment between views, which is it's a paper that basically does a lot of what DINO did, but without teacher student. It uses these auxiliary losses, and they're primarily there to sort of make sure the space is nicely separated and clustered. It's got positioning innovations that it's just borrowed from language, and it does some curation of the data set, and it slightly modifies the transformer architecture. So you can see they've really touched upon a lot of different ways to innovate on this as they've gone along. So prototypes, essentially, we've got classes typically when we're doing supervised learning. One of the things about classes is they're kind of reductionist. So a cat is a cat, but no one's got time to say this is the front paw of a cat, this is the tail of a cat when they're labeling these images. And as a result, you get these fairly discrete labels. They're not hierarchically organized, and they're, as I say, they're discrete rather than continuous. What DINO learns through its self-supervised mechanism is it tries to essentially find consistent clusters of activation patterns that represent different things that it sees in the data set. So for example, instead of cat, the prototypes that you might learn, you might have some prototypes which activate when you've got quadrupedish, you might have some when you've got mammalish looking things, you might have some when you've got foreground versus background, you might have some for eyes or fur and so on. And essentially, these take the place of the classes. And then the tricky thing that you're trying to, well, there's lots of benefits to doing this. First of all, it's sort of continuous. It's distributed, so it's slightly more robust. It gets to learn whatever it can essentially differentiate in terms of hierarchic structure, in terms of the different sort of distributions of pixels that it finds in the data set. And it learns some of the ontological relationships that things have. So this is like that. These things have those things, and we'll see some examples of that. Yes. Yes, I'll covered completely. There's some drawbacks, however. The principal one is, if you've got no labels, how do you show better to the network? How do you know the network is doing well when all it's doing is going, I'm going to create a distribution in response to this input? So one of the interesting things is you would think that once you've trained such a model, you've got all of these useful prototypes, meaning different things, and all that they would do is just train a multi-layer perceptron and basically say, okay, these things will activate when cat activates. However, what they've actually found for the most part, and it seems very empirical, I suspect someone will go back and review it at some point, is chopping off the prototypes. Basically, what you have is a backbone for which you can train a new classifier or a new task head of whatever you want it to do. And because the prototypes are focused on achieving a specific sort of loss function, they're actually not ideal for doing your specialization, creating new task heads. So people just basically what the prototypes ensure is that the backbone and the latent space of the tokens has learned this nice hierarchic, well differentiated space.
So I understand with supervised learning labels, how you can like distinguish a label. This one has gone through and marked it, and you know all these images should cluster here.
Yeah.
When you're talking about prototypes, because there are no labels, what is actually a prototype? It's just a pattern on an activation map?
Yes, it's literally a pattern in an activation map. So here is an example. On the right, we have a supervised fit. One of the cool things that came out of DINO, and this is DINO 1, which we'll see there are two further versions which improve on this. And essentially, one of the things it figured out is that quadrupeds are kind of quadrupedy. And they tend to have bodies and they tend to have legs, and a lot of them have tails, and most of them have necks and heads and so on. And so they do a t-SNE on a labeled supervised fit. And what they find is the animals, regardless of body part, so pixels relating to a horse neck will go with, or patches relating with a horse neck will go with patches relating with a horse body, a horse leg, but they are separated and distinct from a different animal. So it's learning animals the hard way, essentially. Whereas when you've got the self-supervised bit, what it's learned is that not only is there this pattern or family of distributions that seems to relate to quadruped, but then you've got these distributions within these quadrupeds that reliably and consistently relate to body parts. And as you can see, this is a much stronger representation of what an animal is than just the label horse can give us a signal to a purely supervised approach or even a weakly supervised approach.
I'm trying to see if I can see any clustering of specific animals. I can't.
No, for the most part they don't. That's the point. There's and some of these clusters will also relate to, for example, the view, the angle of view, or the posture of the creature.
Yeah.
So it's not even. It's a really shallow and fragile representation relative to the representation that the self-supervised model lets. I think that's. So Mark is asking us to press on, so I should try to do so. So what we're doing with DINO, and in comparison with, for example, like another self-supervised foundation model technique such as masked autoencoding, is rather than deriving our losses from the pixels, we're deriving our losses directly from the prototypes, which means that there isn't like an easy reconstruction target of what should the pixels in this patch be. Instead, what we're trying to do is learn the prototypes that the pixel patterns map to. And the way that DINO does it is it takes a teacher and a student. I can just jump a bit further on here so we can actually see the thing. So essentially what we do is we take a teacher and a student. We can literally bootstrap this whole process from randomly initialized variables, which is amazing. And we have some data, a batch of data. We run some of that batch of data through the teacher, some of that batch of data through the student. We get a softmax of these prototypes at prototype activations. Remember, they're just classifiers without labels, essentially. And we perform a loss on them such that the teacher is doing something that the student has to be like.
So you say prototypes without labels, you mean you've created some arbitrary number of outputs?
Yeah, it's a classifier head where the elements don't mean anything.
Oh, that makes sense.
Well, that's in DINO 1, then 256,000, then yeah, it's very empirical.
It's really large. Not that you will have labels, but you can have something really.
So what they do is they work out these principal losses. There's some additional ancillary losses which are used to make sure that what the teacher produces is nicely distributed as a target. But essentially, after each iteration, they will take the student weights, having done the backward pass and the optimization step, and they will do an exponential moving average to slightly update the teacher. As you can see here, if we were to just replace the teacher with the student each time, then we get this very jumpy around sort of arbitrary changes in target. Whereas as we increase the degree to which we are keeping the teacher weights, you really smooth out this target. The target's still moving, but it's providing a sort of stable target to aim at over successive iterations. And typically they use values like 0.996 or 0.999, which means that they are learning very slowly compared to traditional methods, but they're learning very stably. And essentially this provides this sort of asymmetry, which allows the student to keep learning essentially without collapsing to nothing. Although, as we'll see, there are auxiliary losses which are added to make sure that it doesn't collapse. I can skip this one just for time. All I'm trying to show you is there's a lot of back and forth in the literature between the various DINO iterations and other models which are doing similar things. So coming to data set, they started off just using ImageNet without the labels. By the time they got to V2, they wanted to curate their own data set. And by the time they got to V3, obviously, they created a much bigger data set again. And what they do to make sure that the data is well distributed is they just do this big hierarchic k-means clustering, where they will separate the data into clusters of 200 million, then separate those into clusters of 8 million, then 800,000, 100,000, 25,000. And this way they're saying, well, okay, we've got this much bigger data set. Instead of training with noisy data and bias in certain categories, we're going to try to have this evidence-based sort of balance to the data set. They have a bunch of model sizes. I won't go through all of these. Suffice to say, DINO 1 started off at 85 million. DINO V2 went to 1.1 billion parameters. And DINO V3 is pretty small by foundation model standards. It's still only 6.7 billion parameters. But each time, what they are claiming is that they get new emergent properties by upping the scale. So one of the things that they had to add, so in DINO V1, they found that they could basically do unsupervised segmentation because the class activations, the patch-to-patch activations were so clean. So, but with DINO V2, they started finding these weird spikes of noise in a different range of activation values. And they reasoned that essentially the larger model is learning to do a trick, which is to take some of the uninformative patches and stick some useful information in there for it. So it's basically treating them as registers. And so they added these register tokens here. And the register tokens, they are not directly trained, but instead they're indirectly trained by the class token and the patch tokens. And essentially what it does is, if we look here, you can see if we've got no register tokens, we've got patches that are far away from the dog that are being spiky and used for things. And as soon as we introduce register tokens, those clean up very nicely. And this is very important for being able to use DINO or other sort of unsupervised segmentation models, is that you've got these clean activations at the patch level. So there's two main losses. The first loss is the DINO loss. In fact, both of the losses are basically just your standard cross-swaps and jig. And essentially what we have with the DINO loss is we take a couple of global patches and a few local patches. The teacher only sees the global patches. The student sees the global patches and the local patches. And essentially what we do is we do cross-entropy between, we never do cross-entropy from the teacher seeing any given patch and the student seeing the same patch. We're basically, with the global patches, we're learning to understand the relationship, how this other patch is like the patch that the teacher is seeing. And with the local patches, we're learning how these local patches map to the global patches. So essentially, we're learning how these patches relate to each other such that we want the prototypes to output consistent values. The second loss that we have, this came from the IBOT paper. And this is a little bit like the masked autoencoder loss, except we're operating on the patch latents rather than operating on pixels. So essentially with this loss, again, it comes from language modeling. So it's called masked image modeling. We mask out some of the patches on the student, and we essentially just compare the on a token by token basis, we compare the token to prototype signature again with the one that the masked patch or the student generates for the masked patch. So instead of comparing the pixels that get reconstructed, it's reconstructing essentially this prototype signature. Mm-hmm.
Is this like would this almost be like the equivalent of like dropout for the inputs instead of neurons, because you're masking out specific patches and asking it?
No, that's more about learning a robustness of representation. So when you're doing dropout, you're essentially doing kind of ensemble learning within a network. But this is the thing that this is most like is reconstruction, but not at the pixel space, but instead in the kind of in the prototype space. Yeah. Then there's a whole bunch of ancillary losses. Given the time, I'm not going to go into detail about these. All of these are basically here to make sure that whatever pattern of activations you get out of your prototypes aren't too sharp, so they're not too Dirac-like, and they're not completely flat. So it's basically not saying I think it's a bit of all of these things. And essentially they start off with this centering and sharpening. Centering is trying to make it not too flat. Centering is trying to make it not like a Dirac. Sharpening is trying to make it not too flat. They then replaced it with this other thing, the Sinkhorn NOP, which essentially, I'll just gloss over these. You can read them in the paper if you're interested. But essentially these, again, they just get borrowed from other papers doing slightly different things. And then there's this other regularization term here. So this basically says within a little mini batch on a GPU, let's try and spread everything out around this unit sphere so that we're not too clustered and we're not too separated. And then finally, so this is perhaps the most empirical part of the paper. What they realized is that the segmentation term kind of tops out and then starts getting worse after about 200,000 iterations, whereas classification continues to increase. So after they've done 1 million or so iterations of training, they then basically go back to a teacher from about iteration 200,000 or so. They use that as a teacher for another 20 or 30,000 epochs, except they'll kind of select different ones at different points of this.
This strikes me, is it like trying to generalize through, like, as you said, heavy engineering and hacking to get things to fix, as opposed to like about neuromorphic computing or
it's a very engineering effort.
Like, it's not doing it in the most efficient way. It's like, what can you do if you have like infinite resources and infinite like huge amounts of resources and huge amounts of data?
Yeah, well, I mean, if you're meta, you can do that. Although this is a very modest research effort. I mean, the DINO V3 was like 65,000 hours to train the big model. DINO V2 was like 22,000 hours. So by foundation model standpoints, they're very lean and mean, to be honest.
Working in the direction of how do we really make these things generalized? If you need to work this hard for it to kind of get.
It's not. I mean, one could argue the opposite in ways. Like it might make it It's like when you say we make it generalized, what you mean is like we understand how we generalize. So that generalizes quite well on the image domain. We just have no clue what's going on.
What we're trying to do with these, what they're trying to do is.
Put it in an equation because there's a lot that's completely arbitrary. These parts, like let's take a random number from when we are training last week and stick to this one.
Yeah.
I mean, if you wanted to give it a headline with all of these self-supervised approaches, it's to what extent can we brute force a world model? To what extent can we brute force high-level semantics just from the texture? But in any case, I mean, essentially what they find when they do this is because the classification task is still being learned via the DINO loss, the first of the principal losses, what they find is that when they tack on like 20 or 30,000 iterations of this, they get to clean up the patch activations. And here they're actually doing patch activations at a higher resolution. So that you can select a patch that is on some part of an image, and the semantically similar parts of the image will have fairly clean attentions between that patch and the other patches. So they've changed the way they train things. To begin with, DINO was training foundation models that were both bits and convnets. When they came to V2, they couldn't do that anymore simply because the IBOT loss is a transformer-specific loss. So they kind of dropped the convnet side of things and they trained their smaller bits by distilling. By DINO V3, they decided to train smaller bits and convnets by distilling. Now, the rationale for this is if you get emergent properties at scale by training models at scale, but you cannot get them by training smaller models, your best chance to keep any of those emergent properties is to hope they survive the distillation process. And so this is essentially what they're doing. They provide as good a results as anybody has provided around distilling from VITs to convnets, but I still think they're mainly doing super well on X-rays, which are kind of very texture heavy. So I don't think it necessarily still, you're not going to say, fantastic, I can start using convnets again if you've got a GPU budget to run one of the VIT models, because they still don't match performance. So there's too many results in this paper to show. I'm just going to focus on the big picture and some specifics as well. So they don't do an awful lot of direct comparisons with predecessors, which are annoying. Instead, what they're focused on is look at this cool new thing that our model can do that other self-supervised models couldn't do before. And that changes over time. So image retrieval, copy detection, video instance segmentation, semantic segmentation, that's what DINO focused on. Then they're moving into instance recognition, depth estimation, outer distribution, detection, and part matching for V2. And for V3, they do some more of these things. And they even do they make DINO V3 multimodal by doing a quick kind of cross-modality train with the actual labels from ImageNet, and show that its ability to do unsupervised object discovery, whilst not as good as, it's let me start again. Its ability to do zero-shot tasks involving language prompts isn't as good as the supervised state-of-the-art in terms of classification. However, it's significantly better for semantic segmentation. So it immediately jumped to the state-of-the-art in terms of prompt-based semantic segmentation whilst being behind in classification. So yeah, this is really the only proper comprehensive bit of ablation study they do. That's for DINO V2. They didn't do one for V3. Here's an interesting thing. So VIT B16, 14.2 million versus 1.96 billion on the data set, and 85 million parameters versus 6.7 billion parameters. It's not exactly, changing the world by order of magnitudes. What's interesting about DINO is that the mechanism that gives it a strong representation is kind of there even in the small models, and the scaling up of the models, because they don't show it in the results, we can't really see to what extent it isn't just a matter of we added more parameters and it got better. But what they do show here, for example, there you go, that thing's in the way again. What they essentially show is that their big story is once upon a time, self-supervised was garbage compared to weakly supervised, but look, we're almost there now. And that's essentially the take-home message that they want for V3. Just to conclude super quick, it took less time than Dave, thank you. DINO is a family of purpose-built foundation models. They really are built specifically to do this foundation model stuff. And that's all I'll say for now, actually. There you go.